Good evening, everyone. This is the third problem solving session for the NPTEL course Gasdynamics Fundamentals and Applications. I am Onindo, a PhD candidate from ISC Bangalore, and so today we will be the topics of discussion are related to stagnation and critical properties, which so we'll be looking to the problems related to that. So before we begin, does anyone has any questions or doubt related to anything? Hello. Yes, Rohit, you have something to ask. uh, okay, normal shocks will will that's the part of week 4 lecture content, so better we'll discuss about that in the next Friday session. So today let's just focus on the stagnation and critical properties, but at the end, if we have time, we can go through your doubts. Okay, all right. Okay, and Rohit, if you don't have anything to ask, please unmute yourself so that we can start with the session. Okay, all right. So let's start. Okay, so first let's have a recap of the formulas related to what is stagnation and what total conditions. So at a, let's say we have fluid at state where the, let's say the temperature is T, pressure is P. So these are static temperature, static pressure, and velocity V is brought to rest, or we can say stagnation state, which means velocity is equal to 0, right? And that is done isentropically, which means that by a adiabatic and reversible process. Okay, then the state properties that we get, that is what we refer to as a stagnation or total properties, right? So so remember that these stagnation properties are again defined at a state corresponding to a fluid state, and as the fluid like the flows moves from one state to another state, this stagnation and these total properties might change or might not change depending how depending on the process it undergoes. Okay, so like the static and stagnation condition, like that we can say thermodynamical equivalent condition defined at a state point. Okay, how do we define get that? So first we do energy balance. So we have enthalpy plus kinetic energy, and the stagnation state, we have just enthalpy because the velocity is 0. So this is what we call as stagnation enthalpy, right? And now when we apply the calorically perfect gas assumption, can write this way, and then we get the stagnation temperature T0 as static temperature plus V square by 2 Cp. Okay, and now if we do some algebraic manipulation, put the value of Cp in terms of R, and write the velocity in terms of Mach number times the speed of sound, and if we do some this algebraic manipulation, the final form we get is that T0 by T is equal to 1 plus gamma minus 1 by 2 m square. Okay, so this is the ratio of stagnation temperature to static temperature at a point. Okay, so again the stagnation properties are properties defined at a state point. Okay, and so just note that, so while deriving this formula for stagnation temperature, we haven't yet invoked the assumption that it is reversible process. It is just like what goes in here is that it is adiabatic. Okay, that like we just one assumption is near, that is an adiabatic process, that is there is no heat transfer and no obviously there is no work transfer involved. Okay, so but now if you want to get what is the value of stagnation in pressure, then we need to invoke the isentropic assumption, so that we can write the isentropic law, that is this thing, right? So this, from this we get the ratio of stagnation pressure to static pressure. Okay, all right. So these are the formulas we will be important formulas. So so let's start with the first problem. So here we have an air flowing steadily through a duct shown. So the schematic of the duct is shown. So this is like what we'll know in detail is, looks like a, this is like a CD nozzle. Okay, so you have a converging section, then a small constant area section called throat, and then a diverging section. Okay, so at the inlet at station 1, the pressure, the static pressure and static temperature is given, and the velocity is also given. Okay, and at the outlet we have the exit Mach number given, which is 1.3, and also the exit stagnation conditions are given. Okay, at the exit stagnation pressure and temperature is given, and at the inlet static temperature and pressure are given. Okay, so I guess the problem is clear. So first part is very simple. We have to find out what is the local isentropic stagnation pressure and temperature at the inlet. Okay, so we have to first find the stagnation temperature and pressure. Okay, so we have seen that if you just apply the energy equation, so the formula for stagnation temperature is this: T plus V square by T01. Basically we have to find stagnation temperature at station 1. So T01 is equal to T1 static temperature at station 1 divided by V1 square by 2 Cp. This you can use this formula, or the other formula is this one in terms of Mach number, which is 1 plus gamma minus 1 by 2 m1 square, right? So for this we have to first find out the Mach number and everything, but we can use the left one now, which is this will be easier to do, right, because all the values are known. So the temperature is what is the temperature given? Temperature is given 60 degrees centigrade, which means 60 plus 273, 333 Kelvin. Velocity is given 183 meter per second, 183 divided by, and Cp is 1005. Okay, so if we do that, we will get stagnation temperature is approximately 350 Kelvin. Okay, all right, yeah, 350 Kelvin. Okay, next is stagnation pressure. So this is P, you can do P01 by P1 is equal to T01 by T1 gamma by gamma minus 1. Okay, so here the assumption is that we are bringing the locally at that, from that state we are taking the fluid to rest by an hypothetical isentropic process to get the stagnation pressure, right? So we are using the isentropic relation in terms of pressure and temperature to get the stagnation pressure value. So this is T01 by T, this is 350 by 333 into 1.4 by 1.4 minus 1, and P01 is what we need to find out, and P1 is given as, what is the value of P1? 350. Okay, so if you solve this, we will get stagnation pressure as 415 kilopascal. Okay, so obviously we know that it is expected that the stagnation temperature and stagnation pressure will obviously be like greater than their corresponding static values. Okay, so the first part is done. So where we found out what is the stagnation, local stagnation pressure and temperature. Okay, so you can also, as I said, you can also proceed by this formula. First find out what is the Mach number, and then find the total temperature and proceed and the total pressure using the isentropic relation. Okay, all right. So coming to the second part we have to find out now the static pressure and temperature at the duct outlet. Yeah, 415 or 416, it's close. Yeah, okay. All right. So next is we have to find out the static temperature. Okay, so at the inlet, so at the outlet we know the Mach number and the stagnation condition, right? So here we can use the other formula, this one, that is T02 by T2 is equal to 1 plus gamma minus 1 by 2 m2 square. Okay, so what we know is T02, which is 350 Kelvin, T2 is unknown, 1 plus 1.4 minus 1 by 2, Mach number is 1.3, right? So we can solve this. This is, you will get 262 Kelvin. Okay, all right. And similarly, in the, to find out what is the stagnation, like static pressure, so we can again use the isentropy relationship between the stagnation and static states. P02 by P2 is equal to T02 by T2 whole to the power gamma by gamma minus 1. So P02 is given as 385 kilopascal, T02 is 350, T2 is 262, 1.4 by, all right. So if you solve this, we will get P2 as 139 kilopascal. Okay, so these first two parts are the simple applications of the concept of and the formulas related to static, in like in the, how we do in like compute stagnation properties given static properties, and compute static properties given the stagnation properties. Okay, all right. So what we have seen here, like this, just want to note that these ratios, this is a function of Mach number and gamma. Okay, like both, if you see, like the ratio of stagnation to steady state is a function of Mach number and gamma, right? Okay, so since like in this for air we know this gamma is constant, so you know gamma is 1.4, so this like ratio becomes just a function of Mach number. Okay, all right. Okay, so next we'll look at the next question. So first, this is like what is the question, what is the change in entropy. Okay, so this was part B. Part C is change in entropy. So which formula should we apply here? Delta S S2 minus S1 . Now anyone of you can unmute and say. What we know from base thermodynamics, second law of thermodynamics, that we can, this is Cp ln T2 by T1 minus R ln P2 by P1, right? Is the formula for in change in entropy, right? So this is 1.005 ln T2 by T1 minus R ln (139 bus). What was thing? Yeah, 350. All right. So what we get is, sorry, this will be 0.287. I have written Cp in kilojoule per kg Kelvin. So R is also, R should also be in like 0.287. Okay. So we will get approximately 0.0252 kilojoule per kg Kelvin. Okay, so what we see here, there is a increase in entropy in this process. Okay, so now let's so what are the from second law of thermodynamics, what do we know, what are the two contributions that can lead to change in entropy? So we know like delta S can be equal to delta S due to heat transfer plus delta S due to irreversibility, right? Okay, so this is the first term is basically the heat transfer rate divided by the temperature at which the heat transfer occurs, that is the delta S, that is delta S due to heat transfer. All this is also, the first part is reversible and the second part is like the comes due to the irreversibilities, or what we call is the entropy generation term, right? Entropy generation because of the irreversibilities or losses in the system. Okay, if we note here, for this question we will see that the stagnation temperature at the outlet is 350 and the stagnation temperature at inlet is also 350. Okay, what can we conclude from this? Yes, right, there is no heat transfer. Okay, so implies that no heat transfer, which indicates that the process is adiabatic. Okay, so one thing to note there, if process, if the flow is adiabatic, just remember, just adiabatic, just this point is important, stagnation temperature, yes, for this problem the entropy change is because of the due to irreversibilities. Okay, stagnation temperature stays constant. Okay, so we can just also prove this. Okay, so this is a very important thing. So whenever we say that, let's say we have two sections 1 and 2, if the stagnation temperature at section 1 is equal to stagnation temperature at section 2 for a calorically perfect gas, this is also important, calorically perfect gas. Okay, then the stagnation temperature stays constant. Okay, so we can also prove this. Let's say what is the, let's say we have the total energy at station 1, and on the right hand side we have total energy at station 2, H2 plus V2 square, and let's assume we have some heat transfer. Okay, so now this we can write as, so H0 plus V1 square by 2, this is my stagnation enthalpy at station 1, and this is my stagnation enthalpy at station 2, right? And plus we have some heat transfer. Okay, let's say heat transfer to the control volume is Q dot. Okay, now if Q dot is 0, which means that the flow is adiabatic, right? We see that H01 is equal to H02, which means that first of all stagnation enthalpy stays constant. Okay, so this is true, so that when the flow is adiabatic, stagnation enthalpy stays constant. Next, when we put in the assumption of calorically perfect gas, so in like all throughout the course, this is the remember that this is the assumption that will go on everywhere, that we are dealing with calorically perfect gases only, which means our Cp is constant. So if we do that, we will get Cp_T01 is equal to Cp_T02, which implies that T01 is equal to T02. Okay, so when the so this happens when we have the adiabatic flow, the stagnation temperature stays constant for a calorically perfect gas. Okay, that is what I proved here. Okay, so I think one more. So now what we can say for this thing is that the coming back to this change in entropy part, we say there is no heat transfer, the process is adiabatic. Okay, which means that delta S due to heat transfer is 0. Okay, which means that the entropy change is because of irreversibilities. Okay, all right. Okay, so we can, so for this problem we can definitely say that this is due to irreversibilities. Okay, all right. Okay, so I think we have last one part of the problem, which is we have to now draw the state points on a TS diagram. Okay, so let's see, first let's look at the both stagnation and static state points. Okay, so to insert a slide here. Okay, so to draw a TS diagram. Okay, yeah, we'll see what we get. Okay, so let's say this is our state point 1. Okay, so this is our T1. Okay, and we have a this is our constant pressure line, right? P1, right? And for the stagnation state, this will be our stagnation state, which we write as 0, 1. Okay, and this is our stagnation pressure line, right? So this is T01. Okay, right? This till this part is clear. So we drew the state point. Thus this is 1 is the static state point, and 0, 1 is the corresponding stagnation state point. Stagnation state point. Okay. So next is we have to draw the state point 2. Okay, so state point 2, we know there is a increase in entropy, right? We have seen that the entropy increases between state point 1 and state point 2. So obviously state point 2 will lie on the right of state point 1. Okay, and one more thing is that let's see what is the static temperature value. So we have seen that T1 is 333 Kelvin. No, there is no stagnation temperature change, but there is static temperature change. See, so you in our case the static temperature T1 is 333. So just let me write the values here. So T1 is 333 Kelvin. T2 is, what do we calculate? T2 is 262 Kelvin. P1 is 350 kilopascal. 350, right? 350 kilopascal, and P2 is 139 kilopascal. All right, yes. Okay, so obviously, so this state point 2 will lie slightly below state point 1. Makes sense, because T2 is less than T1, right? So this will be my state point 2. Okay, and this my, so the, we know the pressure line goes like this, right? So this will be my P2. Okay, so now also we see that the P2 isocontour, P2 constant pressure line is lying sort of below P1, so obviously P2 is less than P1, that is also we are getting. And also between these two process we see that there is a change in entropy happening, increase in entropy happening. So this is our, let's say, the process. Okay, now we have to draw the stagnation state, okay, corresponding to 2. So at 2 what we know is that T01 is equal to T02. So let me just extend this line and we'll do this. So this will be our stagnation point 02. Okay, and this will be my P02. Okay, is the TS diagram clear? Any doubts? Yes, stagnation values in terms help us to find what kind of entropy change happens. Okay, also stagnation value by like expressing the state point as when we express a state point as, like, let's say just with stagnation properties, we don't need to explicitly specify the velocities, because that is like the kinetic energy part is imbibed into it. Okay, now what is this vertical thing? This, if we say what is the difference between this part, what is this distance indicate? This is basically v1 square by 2 cp. If we go back to this equation, we look at this equation, we see the difference between stagnation temperature and static temperature, that is v1 square by 2 cp, which is like, this is sometimes we call, I think, velocity temperature, like, because this has v1 square by 2 cp, that has the units of temperature, right? But that is coming from the kinetic energy part. Okay, so this is sometimes referred to as velocity temperature in some cases. Okay, so this vertical part, this thing is v1 square by 2 cp, and again, like here, this T02 minus T1, this vertical distance, this is equal to v2 square by 2 cp. All right. Okay, okay, fine. So I see that this is what happens when the okay, stagnation temperature, we found out stagnation and static temperatures, like how to find out stagnation conditions from static conditions, and to find out static conditions from given stagnation conditions, and also looked at, for this problem, what is important takeaway: if the flow is adiabatic, the stagnation temperature remains same at all the states. Okay, okay, but in addition, but we have seen here that the flow is adiabatic, so T01 is equal to T02, but the flow is irreversible, which means non-isentropic, right? Because we see that we have an increase in entropy, and that's why we also see that the total pressure decreases. You see from the diagram also you can see that P02 isocontour is lying low below the P01 P01 contour. So P02 is less than P01. That is also what we have found out, right? We see that P02 is 385 and P01 we found out as 415 kilopascal. Okay, so P01 is greater than P02. Okay, now in subsequent problem we'll see that in addition to this, if we impose that the flow is also isentropic, then the stagnation pressure also stays constant. Okay, so we'll come to that. So this, understanding these concepts about like having clarity about the stagnation and like the concept of the stagnation condition is important, okay, before we delve into the other concept of compressible flow. Okay, so try to get a very good grasp on and clarity on the concept of the stagnation quantities. Okay, right, okay, because these are very important into, so like basically instead of now in most cases instead of expressing in now we have seen that mostly in cases like thermodynamic processes we express the state points using temperature and pressure, static temperature and pressure. Okay, now in compressible flows it's more relevant to express this in terms of stagnation quantities. Okay, all right, any questions so far? If not, we can move on to the next problem. Okay, thank you. Okay, so the question said that air has a static temperature of 25 degrees centigrade. So temperature is 25 degrees centigrade, 25 plus 273, which means 298 Kelvin. The stagnation temperature is 250 Kelvin. So 250 plus 273, 523 Kelvin. What is the Mach number? Okay, so question is what is the Mach number? So what we will do here, so we know the relation T0 by T is equal to 1 plus gamma minus 1 by 2 m square, right? So here we know T0, T and gamma, so m is the unknown, so we just rearrange this equation. T0 minus by T minus 1 is equal to gamma minus 1 by 2 m square. So I'm just changing sides, so m square equals to 2 by gamma minus 1 T0 by T minus 1. So m is basically square root of this thing, right? You have to take square root of this. So m is equal to, yes, you will get 1.94. 2 by 1.4 minus 1, T0 is 523, and remember always to convert the temperature in to the Kelvin scale. Okay, because the whenever there is temperature ratios, it is important that you have like all the temperature expressed in the Kelvin scale, right? Okay, so we will get Mach number as 1.94. Okay, okay, so all right, so this is, hope this is clear. Let's move on to the next question. Question 3. An airplane flies with a speed of 965 km per hour at an altitude of 16,500 feet, where the temperature is minus 18 degrees centigrade and the pressure is 54 kilopascal. Okay. Okay. Now it's coming up, right? Okay. So again, I will read it again. We have an airplane flying at a speed of 965 km per hour at an altitude of 16,500 feet, where the local temperature is, so the temperature is minus 18 degrees centigrade, or 273 minus 18, which is 255 Kelvin, and the pressure is 54 kilopascal. Okay, so we have to find out yeah, what temperature and pressure might you expect at the nose of the airplane. So what will be that? What will the temperature and pressure at the nose of the airplane? How do we compute that? Yes, it will be stagnation temperature. Okay, so let's just draw a schematic of the airplane. So we have the airplane, right? Okay, so let's say we are looking the frame attached to the airplane, so we have this flow coming, so V is 965 kilometer per hour. Okay, so we have to find out here the nose what is the temperature and pressure. Okay, so this is basically a stagnation point, right, because velocity is 0, right? So basically here here the fluid, like the flow will be the flow will be brought to rest just near the nose. Okay, so the locally the temperature and pressure here will be stagnation temperature. Okay, stagnation condition at the nose of the airplane is a stagnation point in which is saying that velocity is 0, right, which means that the temperature will be equal to stagnation temperature and pressure will be equal to stagnation pressure, right? Okay, so to find that out first, okay, so first when you get this kind of problems, okay, first you have what you have to do is you compute what is the speed of sound and the Mach number. Okay, why this is important I will tell you. So if you remember, like I was explaining what kind of, when you have a flow over some body, if the flow is what kind of flow patterns you get when, if the depending on if the flow is supersonic or subsonic. Okay, so if the flow is like supersonic upstream, so sorry 290, yeah, wait, okay, yes, I will get there. Okay, we'll get there, just wait, um, get to the answer. Just okay, so what I was explaining. Okay, so you need, in this kind of problems, when you get this kind of problem, first you need to check what is the flow upstream, like the approach Mach number of the flow. Okay, because if you have a supersonic flow upstream, you might get a shock, as I have explained. Okay, then the stagnation properties will change. Okay, like will exactly, like I will do a same problem in the next class, when, so in this problem we won't get a shock, but we'll get a similar problem next class where we will get a shock and see what, like what change we get. Okay, okay, look, okay, so just let's, without beating around the bush, let's see. So V is 965 kilometer per hour, so we'll get the this is 268 from 0556 meter per second. Please everybody kindly also check the values once. Okay, and the speed of sound is gamma RT, so we'll get 320.09 meter per second. Okay, so you can clearly from this, you can see and anyway see that this is that the flow is subsonic. Okay, right, so there won't be any shock or anything. Okay, so like the flow, if we assume that the from, like, let's say from far upstream to the nose, the flow is isentropic, so that the it goes to the stagnation set isentropically. So we can use the isentropic conditions to find out the what will be the stagnation temperature and pressure. Okay, so again we can use this also, let's say find what is the Mach number. Mach number you will get as 0.8374. Okay, all right, so 0.8, so 0.8 is, as I think mentioned before, 0.8 is the Mach number at which generally most commercial flight operates in the while cruising. Okay, all right, so where was I? We have to find out the, so we can do this T plus V square by 2 CP 255 plus V is 268 square by 5. Can anyone tell what will be the answer? Okay, 268. Yeah, I'm getting 290.7 Kelvin. Okay, let me check this. Just let me compute this again and check. Yeah, we are getting 290.73 Kelvin. Okay, so this is the stagnation temperature, and stagnation pressure you can again find out applying this gamma by gamma minus 1, right? So yeah, I don't have the answer, but just do the calculation correctly, and so this is the formula you need to apply. Okay, so yeah, just 94, yeah, it might be 94 kilopascal, but just yeah, recheck this. Okay, all right. So okay, I will write Shakti's answer only here. I guess 94 kilopascal. Okay, all right. Any questions so far? Okay, then it's clear, I guess. Okay, so again, like I'll put it here. The assumption is here that the okay, thank you, 85 kilopascal. Okay, yeah, do this calculation correctly. Just don't forget to like take the power and all these things. Okay, P01 is equal to 85 kilopascal. All right. Okay, so one more thing here, the assumption is again that the flow is isentropic. That is that the flow from like far upstream to the nose of the aircraft is isentropic. That's why we can is apply these formulas. Okay, remember that these are all these like these stagnation properties are derived based on the assumption that this is the process is isentropic. Okay, all right, I guess. Okay, now moving on to the next question. Air flows steadily in an adiabatic duct. Adiabatic means there is no heat transfer and no shaft work is involved. At one section the total pressure is 345. Yeah, so it's just 297 Kelvin. Okay, it's like it might be coming up because of small round of errors or something, because like we don't like then based on the number of number of significant digits you take. Okay, this might be because of that. Okay, just yeah, but yeah, but remember that both the formulas are valid. Okay. Okay, so maybe if you just take 2 3, okay, yeah, maybe if you just take more decimal, more digits after decimal in the Mach number, you might get the correct answer. Okay, okay, anyways, let's move on. Just 1 second. Yeah, okay, all right. So Yeah, question 4. So air flows steadily in an adiabatic duct. So we are we have an adiabatic duct, means no heat transfer happening, and also there is no work involved. Okay, so when it is said that it is adiabatic, another thing we can like make the statement that this and adiabatic and no work involved means that the stagnation temperature stays constant. Okay, as we have seen that, we have also proved this mathematically, that for an adiabatic flow the stagnation temperature stays constant. Okay, now add one section, let's say when nothing is given, so let's draw some arbitrary duct. Let's say I'm just making up something. Okay, so add one section. Let's say this is section A. My pressure is, let's say, P0A. This is 345 kilopascal, and this is section B. So P0B, this is 465 kilopascal. Okay, now the question is, in which direction is the fluid flowing and what is the entropy change between two sections? So let's address the first part. In which direction is the fluid flowing? Is it from A to B or from B to A? And why? Yes, why? Reason? Yeah, lower pressure. No, it's not always right. It's the we are used to thinking that there is flow only when there is a pressure difference, like the flow occurs only in the direction of from high pressure to low pressure. That is not always true. Okay, like that might be true in case of incompressible flows, but is not true in case of compressible flows. We will see cases. Okay, let's say let's say if we consider diffuser. What happens in a diffuser? You have the flow. Okay, like the velocity decreases but pressure increases, right? So the static pressure at the outlet of the diffuser is higher than the static pressure at the inlet. Okay, so it's not always true that the flow occurs from a region of high static pressure to low static pressure. Okay, this is not true in case of compressible flows. Okay, so keep that in mind. Yes, so we'll come to that. That's what I meant. Okay, so total pressure. So remember that in case of adiabatic flow, either the total pressure will stay constant if there are no irreversibilities, or total pressure will decrease if there are irreversibilities or losses in the flow. Okay, so if you see here, the from going from B to A, there is a loss in total pressure. Okay, so the flow is from B to A. Okay, so now let's explain. I will explain this more clearly with the what was derived in the class called stagnation pressure energy equation. Okay, so I won't go through the derivation like the professor derived it during his lecture, but let's say you'll write the equation. So dp0 by rho 0. So this is stagnation pressure by stagnation in stagnation density. Okay, so I think in the lecture notes it was written in pt. So p0 and pt both are used, can be used alternatively to express stagnation or total conditions. So I'm just sticking with 0 for consistency in dimensions, like consistency in notation. Sorry, dac t0 minus t plus t0 dsi equals to, okay, so this is work done on the system. Okay, so this is the notation used here, dq. Okay, so and so my ds, the entropy change again, like just so the entropy change ds is equal to dac plus dsi. So this is due to heat transfer, and this is due to irreversibilities. All right. Okay. Yeah, entropy must always is in ice. Okay, so we are not dealing with isolated system now. Okay, so just so this is like an, so now whatever we will be dealing with are all open system, not an closed system. Also all are open system or control volume, right? Because there is both mass and energy transfer can happen. Okay, all right. So yeah, so that was like, so we start from that, and then we have already seen derived things and like entropy change for open system, right? So remember that all everything we are dealing with flows now. So everything is an open system, like the control volume that we place, that the system will designate is a yeah, so on which we perform the analysis is a control volume, and it is an open system. Okay, all right. So where was I? So entropy change is these two parts: entropy change to heat transfer and irreversibilities. Okay, so this is my stagnation, pressure, uh, energy equation. Now in most of the flows that we will deal with in the course on, mostly in gas dynamics, is assume that the flow is adiabatic and no work done, no shaft work. Okay, like generally we have seen that this delta q, like this work done, is generally in case of open system is in form of shaft work. So this is, there is no shaft work, so this delta w will be equal to 0. So this means that delta w will be equal to 0, and if the flow is adiabatic means the entropy change due to heat transfer, this is also equal to 0. Okay, so what we left with, dp0 by rho 0 is equal to plus t0 dsi is equal to 0. Okay, so if we now, no, the T0 static temperature will change. We do when the flow, again I will want to remember, I want to say that when the flow is adiabatic, stagnation temperature stays constant. Static temperature can change, but stagnation temperature will stay constant. Okay, static temperature can change. Okay, because there will be like the, what do you say, conversion of energy. Okay, like their conversion of energy between kinetic energy and internal energy. What is static temperature comes up as? Okay, we have internal energy, right? So like the internal energy might decrease and kinetic energy might increase. Okay, so all this like, or you can say that enthalpy, so the stored, or we can say the stagnation temperature staying constant means stagnation enthalpy is staying constant. Okay, and so what is stagnation enthalpy? Enthalpy plus the kinetic energy part. Okay, so the enthalpy can increase and kinetic energy can decrease, keeping the stagnation enthalpy constant, right? So there can be interconversion between the enthalpy and static enthalpy and kinetic energy. Okay, but the total stagnation enthalpy or total enthalpy will stay constant. Okay, so this is just remember this thing. So means adiabatic flow means stagnation temperature stays constant. Okay, so this is very important. This will come up often when we will deal with different like we'll deal with shocks, expansion fan, or relay flow, fan of flow. All when this will come. So this is a very, that's why I said like understanding the how the having a clear understanding of stagnation property is very important in the context of gas dynamics. Okay, so like just you can ask questions if you have any doubts. Okay, let's, so this session is mainly focused on that. Where was I? Okay, so from the stagnation pressure energy equation, putting in the condition that the flow is adiabatic and there is no shaft work involved, we get this. So which is like dp0 by rho 0 is equal to minus t0 by dsi. Okay, and what we know is that since dsi is the entropy change associated with irreversibilities, right, this is always greater than equal to 0, right? So this is basically the energy generation term. So from second law, if we just go back to second law, we know the change in entropy is greater than equal to del q by t. Del q by t is the entropy change due because of heat transfer. Now to make it equal, we write ds equal to del q by t plus entropy generation term, which is because of irreversibilities. Okay, so dsi is basically entropy generation coming up because of irreversibilities and losses in the system. Okay, so this is always greater than equal to 0. So from this we can easily see that this, since dsi is equal to 0, greater than equal to 0, the change in stagnation pressure will be less than equal to 0. Okay, just from this equation, like you can write since dsi is greater than equal to 0, right? So in an adiabatic flow, the stagnation pressure will either stay constant or decrease. Okay, so let's say if dsi is equal to 0, which means that there is no irreversibilities, that is flow is reversible. Okay, or which also means that isentropic in this case, because we have already put in the assumption that this is adiabatic. So if the flow is adiabatic and reversible, which means isentropic, which means that dp0 is equal to 0, which means that p0 is constant. Okay, but if dsi is greater than 0, dp0 is less than 0. Is this clear? Like when there are irreversibilities in the flow. Okay, all right, so let's say okay, so let's, where was I? Okay, let's again come back to this equation. dp0 by rho 0 is equal to minus t0 by dsi. Okay, now we can also now we will just use the equation of state for stagnation properties. Like this is valid, right? P0 is, we know P equals to rho RT, so P0 will be equal to rho 0 RT0. Okay, all right, or rho 0 T0 is equal to P0 by R. Okay, so now if we use this, we can write the equation in this way: dp0 by p0 is equal to minus dsi by R. Is this clear, this step? Okay, so we're just applying the equation of state for stagnation properties. Okay, so now we have, on the left side we have done the separation of variables. Okay, now we can perform the integration. All right, okay, we need to insert some slides here. Okay, so dp0 by p0 is equal to minus dsi by R. Let's say we integrate from, let's say, 1 to 2. Okay, Alright, so if we do that, what we'll get is ln P02 by P01 is equal to minus S2 minus S1 by R. Okay, or we can write this P02 by P01 is equal to e to the power minus S2 minus S1 by R. Alright, okay, so this is like a formula for change in entropy. This is an important formula. So okay, so like this is okay, so this is like S2I by S1I, S2I by S1I. Okay, now since flow is adiabatic, like the change in entropy is equal to change in entropy due to reversibilities. So basically we can write d like ds as d like dsi, like sorry, dsi as ds only. So this is the final formula. Okay, all right, okay, so okay, so now coming back to the question. Okay, so here between A and B, so we have what we have seen that for an adiabatic flow with no shaft work involved, the stagnation pressure will either stay constant or decrease. Okay, so here if we see that the stagnation pressure is lower at state point at station B A compared to B, right, which means that from this logic we can say that from what we see from like the stagnation pressure in stagnation pressure energy equation, that since okay, let me just draw the thing again. So P0A is equal to 345 kilopascal and P0B is equal to kilopascal. Okay, so since P0A is less than P0B, right, which indicates that flow is from B to A, right? Is this clear now? Any questions? Okay, and what else we can say, that there is the flow is non-isentropic, right? Okay, because the stagnation temperature stays is decreasing. Okay, so again one more thing, so two important points. When we say that the flow is adiabatic, we can just say that that the stagnation temperature stays constant. Okay, now in addition to that, if the flow is if the flow is reversible, which means that the adiabatic and reversible, then we can comment about the stagnation pressure, that the stagnation pressure also stays constant. Okay, and the flow is isentropic. Okay, now if the flow is irreversible, which means that there like losses in the system, then the stagnation temperature will decrease in the flow direction. Okay, so this is what the case we are dealing with, that the stagnation pressure is decreasing in the flow direction. Okay, all right, now the second part of the question was we have to find out what is the entropy change between two sections. Okay, so let's say my flow is from B to A, so my station 1 is my B and station 2 is my A, right? Means like flow is from let's say 1 to 2. Okay, so now we can do S2 minus you can use this formula which we derived just now. Okay, just let me this. Okay, all right, so my P01 is 465. Yes, you are right, it is 85.66. Yeah, 465 kilopascal, and P02 is 345 kilopascal. Okay, again, like flow is from 1 to 2. Okay, so now if we, where was the formula? Yeah, so we can do this, like let's say if we look at this expression, that yeah, that my delta S or S2 minus S1 is equal to SA minus SB also, right? Sorry, no, S, yeah, SA minus SB is equal to minus R ln P02 by P01. Okay, minus 287 ln 345 by 465. So my delta S will be 85.67 joule per kg Kelvin. Okay, is this clear? Okay, see, like irreversibilities are like there are losses, like frictional losses. In this case, mostly the friction. Okay, so the one of the like things Adams we do, like we don't consider like the there are like the boundary layer develops right along the duct walls. Okay, so because of the shear. Okay, so that is the cause of that is one of the important cause of the irreversibilities. Okay, mainly the what there's like the friction, what you can say. Okay, all right, shear. Okay, so again, so the important takeaway here is, if the flow is reversible, adiabatic and reversible, which mean isentropic, both stagnation temperature and pressure will stay constant. If the flow is just adiabatic, stagnation temperature will stay constant. If the flow is, if we say that the flow is irreversible, which means that it is non-isentropic, the total pressure or stagnation pressure will decrease. Okay, so it is can also CFC, let's say from this equation, if there is no change in entropy, if the flow is isentropic, obviously P02 will be equal to P01. Okay, okay, so I guess this concepts about how stagnation temperature and stagnation pressure changes depending on the flow process is clear. Okay, just okay, okay, let's move on. Let's look into the next problem. Consider the flow through a rocket engine nozzle. Assume that the gas flow through the nozzle is an isentropic expansion of a calorically perfect gas. Okay, okay, so yeah, again, as I said, like all the problems will do is mostly the working fluid is a calorically perfect gas, and here it is says that we are considering isentropic expansion. Okay, in the combustion chamber, the gas which results from the combustion of rocket fuel and oxidizer is at a pressure of 15 atmosphere and 2500 Kelvin respectively. Okay, so let's just draw a simple schematic, the rocket engine nozzle. So let's say this is our rocket engine. So then we have a nozzle like this. Okay, so this is, let's say, our station 1, and this is the nozzle exit is our station 2. Okay, what is given here is the, so station 1 is just at the exit of the combustion chamber. So P1 is 15 atmosphere and T1 is 2500 Kelvin. Okay, okay, so then we have been given the molecular weight and specific heat of the gas. Okay, so the molecular weight of the gas is sorry, so the molecular weight is given as 12 and Cp is given as 4157 joule per kg Kelvin. Okay, since it's not air, so the molecular weight and Cp are different. Okay, so the gas expands to supersonic speed through the nozzle with a temperature of 1350 Kelvin at nozzle exit. So we have T2, so T2 is 1350 Kelvin. Okay, all right. Okay, so note that one thing, the flow velocity is very low in the combustion chamber. Okay, as we know, like like this, like in yeah, in rocket motors, right? This the fuel is like in, there is no like in aircraft engines or air breathing engines, like there is air flow coming in, fuel flow coming in, and then combustion happens and it leaves. Okay, so it's like with it's like it's flowing. Okay, but in rocket engines, like the fuel and oxidizer are stored, right? And once they burns in, they get accelerated and then get ejected through the nozzle. So just within the combustion chamber and or the inlet to a nozzle, the flow velocity is very low, negligible, or equal to almost equal to zero. Okay, okay. So what we can say from that is like V1 is almost equal to zero. Okay, if that is true, the stagnation pressure will be equal to the static pressure, which is 15 atmosphere, and stagnation temperature will be equal to static temperature. Okay, here I will just, okay, is this clear? Okay, just let me just say this is combustion chamber and this is my nozzle. Okay, yeah. So is this clear why now the at just at the nozzle inlet, my stagnation temperature and stagnation pressure values are equal to the static values? All right, so this till this point is clear, I hope. Okay, now let's go what we need to calculate. Okay, first, what is the stagnation temperature and pressure at the nozzle exit? Now can anyone say what will be what will be the values, or how can we compute that? Okay, once again I have to highlight this point. This is an isentropic flow, isentropic expansion of a calorically perfect gas. We just discussed in the previous problem what happens to stagnation temperature and stagnation pressure in a flow when like flow is adiabatic, reversible or irreversible. Anyone? Which means you have to compute T02 and P02. Okay, so we have given that flow is isentropic, which means that adiabatic and reversible, right? So which means T02 is equal to T01, right? When as I said, if the flow is adiabatic, it means stagnation temperature stays constant, right, for an calorically perfect gas. Okay, so this is this, and what happens, and what about pressure? Again, it is isentropic, no change in entropy, right? So stagnation pressure will also stay constant. Is clear? Let me go back to this formula. This like the last equation. If S2 minus S1 is 0, right? P02 is equal to P01. Right? Okay. So what we can say? If the flow is isentropic, both the stagnation temperature stays constant and stagnation pressure also stays constant. Okay, doesn't change like between two state points. Okay, all right, it's clear. So this idea you should have, like when we can, what we can make comment. Okay, now if the same problem, we would say that if the flow is adiabatic but there is some irreversibilities involved, stagnation temperature will stay constant again, but the stagnation pressure will have decreased. Okay, if there was irreversibilities, or if the flow was non-isentropic. Okay, if you have any questions at this point, you can just ask. Okay, then we can after that we can move on, and we just wait for a few seconds. Okay, so part A is done. What is part B of the question? We have to find out static pressure at nozzle exit, which means we have to find out P2. Okay, how can we find out P2? So like we can apply this like this. The flow is isentropic, right? So we can apply isentropic relation between state point 1 and state point 2, right? Or we can apply the isentropic relationship between the stagnation state and the static state. Okay, so what we do is like we P2 by P02 is equal to T2 by T02 whole to the power gamma by gamma minus 1. Okay, so P2 is what we need to find out. P02 is 15 atm, T2 is given 1350 Kelvin, T02 is 2500 Kelvin, gamma minus 1 by gamma. Okay, now gamma is not known. Why? Because this is not air. Okay, so we can't assume gamma is 1.4. So to compute gamma, there are some other important things given. We have been given the value of molecular weight and Cp. Okay, from that we can find the value of gamma. Okay, so how can we do that? First we can find what is the value of R, the specific gas constant. So that is universal gas constant divided by molecular weight, which will get 692.8 joule per kg Kelvin. Okay, then we can find Cv, which is Cp minus R, 4157 minus 692.8, which is approximately 63464. What is the value? Just a second, let me. 4157 minus 692.8, 642.2 joule per kg Kelvin, and gamma is Cp by Cv, so we will come out 1.2. Okay, so now we know gamma. So basically now P2 will be P02, which is 15 into 1350 by 2500 to gamma by gamma minus 1, right? Gamma by gamma minus 1. So we'll get P2 as 0.372 atm. Okay, all right. Any questions? Is clear, right? Okay, so we just apply isentropic relation to compute the static pressure. Okay, now and then since the gamma value is not known, we compute it from the given values of Cp and first we compute R, gas constant, then we Cp is given, we compute Cv and do compute the ratio Cp by Cv to get the value of gamma. All right. Okay, so part C, you have to find out the Mach number and flow velocity at nozzle exit. Okay, part C. Okay, how can we compute that? Okay, most simplistic way is to, like, let's say we have to find out the flow velocity at nozzle exit. We can do this thing. Let's write the energy balance between the static and stagnation state. So we can do this right. CPT plus CPT2 plus V2 square by 2 is equal to CPT2 T02, right? Static enthalpy plus kinetic energy is equal to stagnation enthalpy, right? So we need to find out V2. So this will be 2 Cp times T02 minus T2. Yeah, Mach number is 2.9. Yeah, okay. So 2 into, so Cp, yes, we can also do that. We can first another way to do is to use this, like you can write the stagnation, the ratio of stagnation temperature to static temperature is equal to 1 plus gamma minus 1 by 2 into Mach number square, right? So we can use that approach as well. So if you do the then you know the ratio of stagnation temperature to static temperature and then you can find out the Mach number, and after you find the Mach number you can compute the speed of sound and do Mach number into speed of sound to get the velocity. Okay, so so that is, but you can also use this approach, okay, like the from the fundamental, like the basic energy balance. Okay, so yeah, both ways are possible. So here I am first, in that approach you will first find the Mach number, then the flow velocity. Here I am first computing the flow velocity, then we'll go into the Mach number. Okay, so Cp is 4157. So V2 we will get 3092 meter per second. All right, and then Mach number is V2 divided by gamma T2, 3092 by gamma is, remember to put the correct values, gamma is 1.2, R was 692.8 and temperature T2 is 1350. Okay, remember in the speed of sound here static temperature goes in. Okay, so M2 will come as 2.9. okay, yeah, just check the values correctly please. Okay, the okay, and okay, just also let me show the other approach. So the, yeah, so Shakti, please check the value please correctly. This, so I took this problem from the book by Anderson, so I haven't checked the calculation, so hopefully I expect that it is correct. So please recheck your values once. Okay, so another way is or other way of solving part C is, so you know T02 by T2 is equal to 1 plus gamma minus 1 by 2 m2 square, or m2 is equal to 2 by gamma minus 1 T02 by T2 minus 1 whole to the power half. So you can do 2 by 1.2 minus 1, T02 is 2500, T2 is 1350 minus 1 whole to the power half. So from here you will get Mach number as 2.9. okay, and again V2 will be equal to m2 into square root of gamma r T2. okay, alright. So just put in, remember that you have to put in the correct values of gamma and r here. It is not so I am getting this 3092 meter per second. okay, so this, if I just go by the, okay, let me just recompute this and see if I am getting this. 4157 into 2500 minus yes, yeah, so that's why that's have to be careful. okay, yeah, no, so V2 is right and this is right. okay, I just rechecked. okay, yeah, so just put, yeah, so remember this is like gamma and r values are different here. okay, all right. Anyway, so these are like the two ways we can solve the same problem. okay, so in the okay, so like this, the fast way is just you apply the energy balance, and like this starting from the fundamentals, you don't like, if you, even if you don't remember the formula, you can do it. okay, that's what my point is. If you don't just don't recollect the formula, still you can do it. yes, okay, yeah, okay, then fine. yeah, so yeah, so this problem is slightly tricky because it is like not air, so the working fluid has different values of R and CP, so just need to be careful if you get this kind of problems in the exam. okay, all right. So any questions? If not, we can, let's move on to the next question. okay, so this is a two-part question. Question 6. So we have a steady one-dimensional flow of a perfect gas with heat transfer. The TS diagram shows both static and stagnation points at two locations. Okay, and so the TS diagram is given. okay, so if like here the stagnation state are represented by the subscript T. okay, so this one subscript T is the stagnation or total condition corresponding to 1 state point 1, and 2T is the stagnation state point corresponding to the static state 2. okay, so any question regarding the TS diagram? It is clear, I guess. okay, and it is given that these two differences are given. okay, that A and B, and it is shown that A is equal to B. okay, all right. So the first question, choose the correct option. There is heat transfer into the system, there is heat transfer out of the system is adiabatic, which means there is no heat transfer, and option D, can't say. okay, so what can you infer from this TS diagram? okay, just for the sake of thing, let's say I will write this as 01 because for the consistency in notation. okay, so this is taken from a different book, so where this stagnation states are represented and by a subscript T. okay, so this is 01 and 02. okay, so if you just project this here, So this is T01 and this is T02. Okay, so what we see here is T02 is greater than T01. Okay, so when can stagnation temperature increase? Because there is heat transfer into the system. Okay, so again let's me write the this thing. So let Q dot is heat transfer into the system. Okay, so again remember this is an open system. Okay, so you can write H1 plus V1 square by 2 is equal to plus Q dot is equals to H2 plus V2 square by 2. This we can write H01 plus is equals to H02. If we write in terms of stagnation temperature, this will be T01 plus Q dot by Cp is equal to T02, right? So if we see here, if T2 has to be greater than T01, which means that Q dot has to be positive. Okay, right? Q dot is greater than 0. Okay, which means that there is heat transfer into the system. Okay, so till now what we have seen, that if the system is adiabatic, yes, stagnation points this like sort of representing the total energy in the like total energy enthalpy plus this thing. Okay, so like there is, if there is, it's like, and that's why the term also total temperature, like it's like total like kinetic energy plus enthalpy, it's summed up. Okay, and that we are representing in terms of temperature. Okay, like to enthalpy plus kinetic energy is the total energy, which is also the stagnation enthalpy. Okay, all right. Okay, so if there is heat transfer into the system, obviously the total temperature or the stagnation enthalpy will increase. Total temperature or stagnation temperature increases, which indicates as total or stagnation enthalpy also increases when there is heat transfer into the system. If it's adiabatic, it stays constant. If there is heat transfer out of the system, obviously the total temperature will reduce. Okay, so I hope this is clear. So the same question, next part. Okay, now choose the correct option. So now the question is what you can comment about the Mach number of this at the two states. M2 is equal to M1. No, it's not right. No. What does A equals to be represent? Okay, what is A? So again let me write this. So this is 01 and this is 02, right? So what is A? A is equal to T01 minus T1. What is that? V1 square by 2 Cp, right? You saw this. And what is B? T02 minus T1. Sorry, T02 minus T2, which is V2 square by 2 Cp. Okay. Now, given A equals to B, what does that mean? V1 is equal to V2, right? So the velocities is equal. Okay, but does that mean Mach number is also equal? No, right? Because what is Mach number? The ratio of the flow velocity divided by the speed of sound. The speed of sound between set point 1 and 2, are they same? Yeah, it's pretty evident from the figure that T2 is greater than T1. So what is Mach number 1? M1 is V1 by gamma R T1 and M2 is V2 by gamma R square root of gamma R T2. Okay, Okay, let's take a ratio of these two, m1 by m2. Okay, so that is v1 by gamma r t1 into gamma r t2 by v2. Okay, so now since v1 and v2 are equal, we can cancel this. Okay, now what we are left with is m1 by m2 is equal to square root of t2 by t1. Okay, right? Now say which is the correct option. No, is m2 greater than m1 or m1 greater than m2? What is this ratio is greater than 1, right? Since t2 is greater than t1, it's evident, pretty evident from the diagram, right? The temperature at state point 2 is greater than temperature at state point 1. Mach number is inversely proportional to the square root of temperature, right? So the correct option will be, that is m1 is greater than m2, which is option C. It's clear? Okay, let me go through this again. No, look at this, what is written in red. Look at this expression. Is it, they just derived it mathematically starting from this. Okay, so a equals to b means what this is. I have written what is a and b, right? A is v1 square by 2 cp, b is v2 square by 2 cp. So a equals to b means the velocities are equal. Okay, right? So Mach number is velocity by speed of sound, or like we can write Mach number is proportional to flow velocity and inversely proportional to the temperature, square root of temperature. Mach number is, so since in this case between state point 1 and state point 2, the between state point 1 and state point 2, the flow velocity is equal. Okay, so the Mach number is only dependent on temperature. Okay, and we see that Mach number is inversely proportional to temperature. Okay, so if you look at the last line, I have taken the ratio of two Mach numbers. Okay, so if I just cancel, velocities are equal, so gets cancelled. So finally what we get is m1 by m2 is equal to square root of t2 by t1. Okay, and from the TS diagram we can clearly see that t2 is greater than t1, right? So from this, like I have shown it mathematically, that m1 is greater than m2. Okay, so this is a very conceptual and fundamental problem. Okay, like it's test your understanding of the stagnation conditions and how and its representation on the TS diagram. All right. Okay, so we have much now, like so all these problems are like quite a detailed discussion of how the stagnation properties are computed, and mainly to for you all to understand how these stagnation properties change in the flow based on different conditions. Okay, all right. Okay, so next part is what we know is the star conditions. So star condition is again like we consider a reference state at a point, right? At a point we consider a reference state like the stagnation state, but here the assumption is, so in this, when we compute the stagnation properties, we assume that we are taking the fluid at a particular state to a state where the flow velocity is equal to 0, and saying what will, and we're taking through a isentropic process and saying what will be the temperature and pressure at that state. So that's how we get the stagnation properties. And similar thing to get the star condition or critical condition, our reference state is where velocity is equal to the speed of sound or Mach number is equal to 1. Okay, what am I writing, sorry. right? So when we are getting stagnation conditions or stagnation properties, our reference state was V is equal to 0. In case of star conditions, our reference state is the that our flow velocity, that we take the fluid from a particular state to a state where the velocity is equal to the local speed of sound, okay, and then say what will be the corresponding temperature and pressure, okay. That gives us the star condition, or star or critical condition. There is the critical temperature and pressure, okay. All right, so the major formulas in this case are, what is the like the we know what is the ratio between the stagnation and static properties, okay. Now the major formulas are the ratios between the star critical and the stagnation properties. So this is 2 by gamma plus 1. So for pressure it is again remember this, all these processes are isentropic, so we can just put in the isentropic relation. All right, so any questions about the stagnation, sorry, the start state or critical state, okay. So again remember, this stagnation and critical states are like thermodynamically equivalent reference states corresponding to the flow state, okay. So we are just equivalent to the given like the state point, we are considering another reference state point, okay, assuming that we take the fluid from that state point to a reference state point, okay. For star conditions, the reference state point is when the flow velocity is equal to sonic velocity. For stagnation conditions, the reference state is that the flow velocity is equal to 0, okay. Okay, so yeah, so these star conditions are also like important, like the importance will come up like more evident when we'll do do analysis on variable area duct flows, okay. So that will I think in weeks, this is week 3, right? Yeah, week 6 or 7 we'll do that, so there will be more, this importance of star bodies will become more relevant that time, okay. All right, so like let's do 1 or 2 problems, okay. All right, so first problem is certain high speed wind tunnel experiments used combustion air heaters to generate extreme pressures and temperature required to accurately stimulate high Mach numbers, okay. These are just general info. So in one of the tests, a combustion air supplies stagnation conditions of 1.7 megapascal and at 1010 Kelvin. So P0 is 1.7 megapascal and T0 is Kelvin, okay. So we have to find out critical temperature and critical pressure corresponding to the stagnation conditions, okay. So we have this formula, T star by T0 is equal to 2 by gamma minus 1, 2 by gamma plus 1, right, which is 2 by 1.4 plus 1. So and the value is 0.833, okay. So one thing remember, that this value, this is constant for air, okay. And similarly, if we do this thing okay, you can say that for air, here gamma equal to 1.4. So this ratio between the critical properties and corresponding stagnation properties, that is constant, okay. Because we have seen here, this is just a function of this ratio, is just a function of gamma, right? So for air we know gamma is 1.4, so we have these values, okay. So now it is pretty straightforward, right? So T star will be it is 0.833 into 1010, 0.833 into 1010, which is 841.33 Kelvin, and P star is equal to 0.528 into 1.7, 0.528 into 1.7, 0.8976 megapascal. Okay. Any question? Is this clear? Yeah. So this is simple, straightforward. So you just need to remember these two formulas. Okay. Ideally, if you need to just remember this formula, and other like the ratio for the pressure and all you can get from applying the isentropic relation, like the corresponding relation for pressure and density you can get from the isentropic relation. Okay, right, because you are just applying the isentropic relation here, that like the pressure ratio is equal to temperature ratio to the power gamma by gamma minus 1, right? Okay, all right. Any question? Okay, great, cool. Yeah, moving on. I think I might have to, yeah, okay. So for prove that for air, m star. So what is m star? So at critical state, right, we can compute this a star, which is gamma r into t star. Okay, so we can, like, this a star is, I think, called the characteristic sonic velocity or sonic speed. Okay, which is basically um, yeah, so which is basically the speed of sound corresponding to the critical temperature. Okay, so we're just putting the critical temperature. So this is not an actual speed of sound, this again a star is some reference. Okay, like we have some, like for static temperature and static pressure we have reference conditions like stagnation properties, or similarly for speed of sound we have a another another reference value, which is a star. All right, which is computed based on gamma RT. Okay, now if we do that yeah, where was I? Yeah, so a star, and then you get the characteristic Mach number, which is m star, which is velocity by this a star. Okay, and our normal Mach number is m equals to v by a. Okay, so this is v by gamma r t star, and this is v by normal gamma r t. All right. Okay, similarly you can compute something called m0. If you just compute a speed of sound taking the stagnation temperature and then do v by that is also give you something called m0, but that is not much of significance. But this characteristic Mach number m star is sometimes used in some analysis. Okay, so our question is, we have to prove that for air this m star tends to approximately 2.45 when Mach number tends to infinity. Okay, so I don't have time, so I won't go to the derivation, but and see the lecture. So there was a formula derived for this, that m square is equal to 2 by gamma plus 1 divided by m star square minus gamma minus 1. Okay, so now if we just rearrange this, taking the denominator on the right hand side to the left hand side, or like multiplying the denominator on the left hand side on both the sides, we'll get gamma plus 1 into divided by m star square minus gamma minus 1 is equal to 2 by m square. Okay, so now if Mach number tends to infinity, if Mach number tends to infinity, what will happen? You see right hand side we have 2 divided by Mach number square, which means right hand side will be 0, right? So what we are left with is gamma plus 1 divided by m star square minus gamma minus 1 is tends to 0. So if we rearrange, we will get m star tends to square root of gamma plus 1 gamma minus 1 when m tends to infinity. Okay, now for air, gamma is equal to 1.4. So if we put these values here, we will get m star tends to 2.4495. Okay, all right. So this is just so what we need to remember is this, basically this when characteristic Mach number tends to some finite value when Mach number tends to infinity or becomes or like goes to a very large value in this case. Okay, any doubts? Yes, it obviously is true for a calorically perfect gases only, because remember this or every which one? So this is true for every calorically perfect gas, this expression in box. Okay, but m star value will obviously change because based on the value of gamma. Okay, any questions, any other questions or doubt you can ask? Talking about which equation? This equation is valid. Obviously this equation is valid. Remember again, as I was saying that this m star is valid. So remember again, like all the most remember all the this equations are derived based on the assumption that it is a calorically perfect gas. Okay, because everywhere you will put like enthalpy equals to Cp into T. Okay, and then like write Cp as gamma r by gamma minus 1, so that you can combine and write like get the speed of sound expression somehow and rearrange all the equation, right? So you have seen in the lectures how we can like, so our basic energy equation is like enthalpy plus kinetic energy is equal to at enthalpy plus kinetic energy as inlet is equal to enthalpy plus kinetic energy as outlet if there is no work or heat transfer involved, right? So now from that you have seen how how using the different like taking the reference quantity as, let's say on the right hand side, taking the reference as as the start state, or taking the reference as the stagnation state, we can arrive at a different set of alternative forms of energy equations. Okay, so like those, like keep those equations in mind, because like those equations will again come up when we'll do or like do analysis on different kinds of flows like normal shocks, oblique shocks, or much later in the course like Rayleigh flows and Fano flows. So these will come up, and in that case we will see how important this stagnation and star properties are. Okay, so that's why like the first it's important you get acquainted with how this properties changes and how they are defined and how to represent them on the TS diagram correctly. Okay, any other question? I think I have 5 more minutes because we started at 5 minutes late. So okay, so I will just do this because it will be important for your help in solving your assignment questions as well. Okay, so one thing is question 9. So you have to determine the maximum speed that can be achieved by accelerating air at standard sea level condition. Okay, so at standard sea level condition, what is given is that pressure of 1 atm and temperature of 15 degree Celsius. Okay, so let's say you have air at air in some reservoir, okay, at a pressure of 1 atm and a temperature of what is 15 plus 270 is 298 Kelvin, right? 298 Kelvin, and you let's say put a nozzle to accelerate it. Okay, so the thing is, what is the maximum speed you will get? V2 max. Okay, so again, since this is in a reservoir, so this this is 1, this is 2. Since this is in a reservoir where the flow velocity is 0, this stagnation state is again equals to static state, which is 1 atmosphere or 101325 Pascal, and stagnation temperature is equal to 15 degrees centigrade or 298 Kelvin, right? This is clear, right? So this is our stagnation state. So now the question is, what is the maximum velocity we can get? Okay, so what is the idea is, so let's say we do this. So let's say we apply the energy equation. So Cp T1 plus V1 square by 2 is equal to Cp T2 plus V2 square by 2. Okay, so now this is basically, you can write V1 is obviously equal to 0, or we can write this as Cp T0 as well, Cp T01 as well. Okay, now for maximum V2, when we can get maximum V2? Okay, so let me write this. V2 is equal to 2 Cp T01 minus T2, right? Okay, so when can we get maximum Cp? Sorry, maximum V2. Sorry, so max V2, T2 has to be equal to 0. Okay, so to get maximum velocity, what is the minimum temperature we can go? Is like 0 Kelvin, right? So this is in Kelvin. Okay, so for maximum V2 we have to, yeah, absolute 0. Okay, so basically V2 is equal to 2 times Cp times T01. Okay, okay, now one thing is that again here the assumption is we are doing isentropic expansion. Okay, so I think you have in the problem one of the questions in the I think second last question in the assignment, we have this, like you have to compute what is the maximum velocity you can attain. Okay, so you have to get it in this way. So you put in like this, so you are expanding the gaseous air to a state where your static temperature is 0. Okay, so you can write this in some slightly defined way, just by like there is, you can write the formula in terms of R as well, write this one. Okay, or yeah, is fine. So these two formulas are there. So like basically V2 max, exactly right, enthalpy is converted to kinetic energy only, so the 0 internal energy or enthalpy. Okay, so V2 max you will get 2 times 1005 into T01 is 15 plus 273 is, oh sorry, 298, right? So this will be 760. What are we getting? I don't, 773. Okay, we recheck that. Yeah, okay, this is 773.9 meter per second. Okay, all right, so is this clear? We have time for this. Okay, just let's go through these ones. I think we have discussed. We can just, so this will be the last question, or is an important MCQ. So we have a flow through a variable area duct. Okay, no work interaction involved. Which of the statements are correct? Okay, so this is a multi-option correct question. So the first question, just let's go through the statements quickly and see which of them are true, correct, and okay. So the first statement: total temperature decreases if a cooling jacket is placed around the duct. Is this true or false? So if a cooling jacket is placed, what will happen? There will be heat transfer out of the system, right? So the total temperature will decrease. Okay, so this is clear to now every one of you. Now we have seen that if it's adiabatic, total temperature will stay constant. If you add heat, we saw in one of the problems that total temperature rises. So if you cool the duct, obviously the total temperature will decrease. Okay, option B, statement B: total pressure stays constant only if the flow is adiabatic. Is this true? So is the flow being adiabatic the sufficient condition for flow to be total? No. Yes. Good. So this is false. So flow has to be adiabatic and reversible, which is means isentropic for total pressure to stay constant. Yeah, good. Okay, next, the value of A star stays constant if the flow is adiabatic. Yeah, this is true again. Okay, as you can see, the value of A star depends on the value of T star. Okay, so T star is a reference state again. Okay, and T star is a reference state again, similar to the stagnation state, right? Okay, so again, and as we have seen, if the if the we have seen if the flow is adiabatic, the stagnation temperature stays constant. Okay, similar way, if the flow is adiabatic, the T star will also remain constant. Okay, because that is derived just based on energy balance. Okay, so adiabatic is the necessary and sufficient condition for it to stay constant. Okay, similarly, so just as stagnation temperature stays constant when the flow is adiabatic, the T star or critical temperature will also stay constant if the flow is adiabatic. Okay, and the A star just depends on, is just a function of T star. Okay, so A star will just also remain constant. Okay, so let's say you have a pipe, so you have some part which is adiabatic, so the A star will remain constant. Then again, some part, if you keep on adding heat, in that part it will the A star will change because T star will change. Let's say again you have some portion which is adiabatic, so again the A star will again stay constant there. Okay, so as long as in between the section of the flow where it is adiabatic, there is no heat transfer, A star will stay constant because T star will also stay constant. Okay, okay, last question: for an adiabatic flow, entropy change is non-negative. Non-negative means it is greater than equal to 0. What about this? Is this true or false? Yes, this is also true. Okay, this we have seen, like we have derived this. So when we have an adiabatic, so entropy change has two parts: entropy change due to heat transfer plus entropy change due to irreversibilities. When the flow is adiabatic, there is no entropy change due to heat transfer, so the entropy change can happen only because of irreversibilities, and that is always, which is entropy generation because of the losses in the system, and that is always greater than equal to 0 or non-negative. Okay, 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 so this is all. Any yeah, so he got like slightly over time today, but I think the discussion today we had will be helpful for you to understanding much better understanding of how the stagnation properties are, and which will be useful again in going into the subsequent lectures related to different configurations. Okay, yeah, thanks. Okay, So just go through everything again. So I have tried to put in all like the problems that sort of have all sorts of combination when these things happen. Okay, so we'll go into much, we'll next sessions, as you'll see, we'll start going to more details about the different shocks and different other oblique shocks and other interesting flow structures and features that we get in compressible flows. Okay, so if we have any doubt, we can wait for some time to clear them, or we can end today's session. Yeah, Shakti, you had some doubt about the shocks. You can ask. If we just let's say, you can ask that. Just give me a minute. Let me. How? Which advection equation? I'm not getting that. Yeah, maybe better we'll. I think we'll take some time to discuss. Maybe we'll discuss this next Friday, because like ideally that is week 4 is next week. So let's discuss about shocks. Yeah, normal shocks next Friday. Okay. All right. Anything else? Yeah. Oh, I think there is someone posted there is some typo in the, I think, the assignment problems. Okay, so I will just maybe post the like correct thing in the discussion forum. So in the, I think in the final problem you have like the last problem, which is very looks very gibberish. Nothing is in that. You have like in the last problem you have been given the stagnation pressure and stagnation temperature, and you have to find out the like the what is there. Okay. All right. So I guess we can end today's session then. Thank you all for attending, and I will see you again next week with discussion on start discussion on normal shocks. So that will be also interesting. Shocks, standing normal shocks and moving normal shocks. So the solving problems and understanding that will be interesting part. Okay. Okay, then have a good weekend and see you all next Friday. Good night.